What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 10, Review Exercises. Let's do it. So for question 1, we're meant to solve the triangle, and we've already got these sides and angles that I put in here. And so we got to find this side, we've got to find this angle and this angle as well. All right, so what we have here is we have a nice law of sine situation. What I always say is try law of sines first, then if it fails, go to law of cosines. Because law of sines is easier, and we do have enough for law of sines. So check this out. I can say sine of 50, this is the law of sines. So sine of an angle over its opposite side, so sine of 50 over 45 must equal, and again, this is legit even if it's not a right triangle, sine of another angle and it's over its corresponding side. So we can say equals sine of alpha over 105, and now we can cross multiply, and we got 45 sine alpha equals 105 times sine of 50. Then we're going to divide both sides by 45 to isolate. Last but not least, I need to get rid of this sine, so I need to take arc sine of both sides. So I say alpha equals arc or inverse sine of this quantity. So let's plug that into Desmos now. And when we plug it in, we get something that says undefined, okay? So that means that this quantity must be outside the domain of arc sine, meaning it must be below -1 or greater than 1. And so that's undefined, which means that this triangle is therefore not possible, and that is how you do it. Boom, done. So for this one, we're going to solve the triangle, meaning solve all the missing components. First, I'm going to solve for this angle because I know triangle angle sum theorem says that all the angles must add up to 180. So 25 plus 36 is 60. Plus C has to equal 180. That means angle C is 120 degrees. Now what I'm going to have to do to get the missing sides is we're going to have to use law of sine. So first, I know that 24 and 16, they're a pair because they're opposite each other. So we say sine of 24 over its opposite side equals, let's go with sine of 36 over its opposite side, which happens to be A. So now we got a nice little proportion. Let's cross multiply and solve. We got 16 sine 36 equals A sine 24. Divide by sine 24 like so. And now we have an expression for A. Let's do that in Desmos. And we got 23.1. So A equals 23.1. The last thing we have to solve for is C. So we can set up another proportion. We can say sine of 24 again over 16 equals this time sine of 120 over the opposite side C. So there we go. There's the proportion. Let's cross multiply. And we get 16 sine 120 equals C sine 24 divided by sine 24 like so. And that's going to give us our value for C. Let's plug it into Desmos. And here we get 34.1 rounded to the nearest tenth. So little c equals 34.1. And here are your 3 answers. Boom, done. A pilot is flying over a straight highway. He determines the angles of depression to 2 mileposts 2.1 kilometers apart, meaning these will be 2.1 kilometers apart, A and B. And he's got the angles of depression here as 25 and 49. That's in the diagram. Find the distance of the plane from point A and the elevation of the plane, meaning elevation would be this red line, and then the distance to point A would be this. So we got some good stuff here. So first of all, I see kind of like this type of a triangle here that we can use. And if this angle is 49 and this little angle here is 25, this little angle in the middle is the difference, which is 24 degrees. And the other thing is, since this is parallel to the ground, right? This is a transversal, which means that this angle here is also 25 because these are alternate interior angles and they are congruent when you have 2 parallel lines. Okay, now we got enough for a little law of sine situation because I can say sine of 24 over its opposite side, 2.1, is equal to sine of 25 over its opposite side, which is the distance to A. And we'll go ahead and call that x. So we'll say sine of 25 over x. Now we can cross multiply and solve. Boom, boom. X sine 24 equals 2.1 times sine 25. Divide by sine of 24 on both sides like so. And we're going to 24, and we're going to plug that into Desmos now. And rounded to the nearest tenth would be 2.2. So distance to A is 2.2 kilometers, and that's our x. And then now we need to figure out the elevation, that vertical distance. So we got some other information here, right? We've got this little triangle in here. We know this side is 2.2. We know this side is 90. And we also know that this angle is 180 minus these two together, aka 180 minus 49, which is 131. That gives us this angle because this is 180 degrees, which means this angle in here must be 49. So now I can use a nice little trig function, right? With that 49, I can say sine of 49 is equal to, and let's call this side y, right? The elevation is equal to opposite, which is y, over hypotenuse, which is 2.2. Boom, I got a nice trig function that I can just straight up use. It's a nice right triangle. Don't need a law of sines. So multiply both sides by 2.2. And this is what I'm going to get for the elevation. So let's plug that into Desmos now. And here we get 1.66 rounded to the nearest tenth would be 1.7. Now they have 1.6. Now here is plugged in with 2.2, but remember 2.2 we rounded up. So I'm actually going to use the exact value here and replace that 2.2. So we're going to use the unrounded value. And then we get 1.64. The reason why I did that is because in the back of the book, they actually got 1.6. So using 2.2 would have rounded to 1.7, but I believe they used the unrounded value to get this. So anyways, 1.6 is the elevation. So we'll say 1.6 kilometers like so. That's how you do it. Boom, done. So for this one, we're meant to solve this using the law of cosines. And since we're starting out with side, angle, side, we know that there's not going to be multiple triangles. There's only one triangle, so we're kind of good to go with just a single triangle. So let's solve for it. So law of sines, if we're trying to find this side first, A, right? It's the unknown. It's the side and the angle that are known, that are opposite each other that we start with. So we start with the side first, opposite that known angle, which is A squared, equals the other two sides squared and added together, minus 2 times the other two sides, 13 and 15. And then we have cosine of that opposite angle, which is 54, okay? So this is going to equal A squared, but I want A. So I'm going to take this quantity and take the square root of it, and that's going to give me A, not A squared. So let's plug that into Desmos now. And rounded to the nearest tenth gives us 12.8 for that side. So A equals 12.8. Now we just have to find the missing angles, B and C. Now to find the angles, I'm actually going to use law of sines now. So we're going to say sine of 54 over the opposite side, 12.8, equals, and I'm going to choose B next, sine of B over its opposite side, which is 15. All right, we're going to cross multiply, and we get 15 sine of 54 equals 12.8 sine of B, like so. We're going to divide by 12.8 and get rid of that there. And then we have to take arc sine of both sides to get rid of the sine there. So we have to take arc sine of this quantity. So let's plug it into Desmos now. So I took the unrounded version of 12.8 and put it in here, and we get 70.98, which rounding to the nearest tenth will bump it up to 71. So we got B is 71 degrees. And last but not least, we got C. But for that, this is nice and easy, right? Because these three angles have to add up to 180. So 54 plus 71 is 125. So what's missing would be another 55 degrees, which means C equals 55. So those are your three answers. Boom, done. To find the distance between two cities, a satellite calculates the distances and angles shown in figure 3, not to scale. Find the distance between the cities. Round answers to the nearest tenth. So the distance here is going to be this red line like so. So to figure that out, let's call it x. Well, we can use the law of cosines because we know the opposite angle. So I can say x squared is equal to one side squared plus the other side squared minus 2 times the product of those sides, 210 and 250, and then times cosine of that opposite angle, cosine of 1.8. And I don't want x squared, I want x, so I can take the square root of both sides and I can get x. Let's do that now in Desmos. And here we get 40.6 to the nearest tenth, so we'll say 40.6 kilometers, boom, done. So for this one, we're meant to plot this point 5 with the r value. Theta is negative 2 pi thirds. So what we do is we find going straight across, negative 2 pi thirds is going back this way, which would be right here, right? As if we went positive, this would be positive 2/3, but we're talking negative 2 pi thirds, which is the same as 4 pi thirds, right? And now that we know we're on this line, then we go out 5, right? So we go out 2, 3, 4, and here's 5, right in between 4 and 6. So there is your point, boom, done. To convert this to regular coordinates, the formula is to take that r value, negative 2, to get the x and multiply it by cosine of the theta value, 3 pi over 2. And then to get the y value, it's negative 2, but instead times sine of that same value. And if we look at the unit circle, right, 3 pi over 2 is right here. Cosine of 3 pi over 2 is 0. So the x-coordinate is going to be 0. And for sine of 3 pi over 2, that's going to be -1. So -2 times -1 is +2. So that would be the rectangular coordinate. Done. So we want to convert this to polar coordinates. So the first way is we have to get our r value. And the r value is going to be x squared, which is 81, plus y squared, -4 squared is 16, the square root of that. So that's going to be 97. So r is square root of 97. Now to get the theta value, theta is found by taking arctangent of the y value, -4, which I'll just say 4 because the negatives are going to cancel out, over -9. Again, that's just going to be 9. And remember, because they're both negative, this is going to be in the third quadrant. Okay, so just remember that. So this might give us a reference angle back in the first quadrant, and then we got to convert it to the third quadrant by adding 180 degrees. So let's check that out in Desmos now. So square root of 97 is 9.8489, and then arctangent of 4 ninths is 23.96 degrees. Again, we have to get in the third quadrant, so we have to add 180, and we get 203.9625, and we get 203.96 degrees. So in polar form, it'd be 9.8489, comma, and you know, the amount of digits they rounded to is sort of arbitrary, but I'm just doing what they did in the back of the book. And then for the theta value, it's 203.96 degrees. That's how you do it. Done. So for this one, I just have this little infographic up here that's going to help give us a little bit of guidance. So first, we're trying to figure out what r is. And so if I can take the square root of both sides like so, I got square root of x squared plus y squared equals 8. And now I see that r is equal to x squared plus y squared, so I can replace that with r. So my equation ends up being simply r equals 8. Boom, done. For the following exercises, convert the given polar equation to a Cartesian equation. So for this one, we're going to start with the formula such that x equals r cosine theta. Okay, so this is kind of a way that we convert rectangular to polar, right? So if I divide both sides by r like so, I see that cosine theta equals x over r. And now I can plug this in for cosine theta. So now I have r equals 7 times x over r. Now what I'm going to do is I'm going to multiply both sides by r, and I got r squared equals 7x. And the reason why this is cool is because r squared is equal to or equivalent to x squared plus y squared. So we can kind of substitute in for that equals 7x. And that's how you get the equation. Boom, done. So for this one, we're going to start with the equivalency such that theta equals arctangent of y over x. So I'm going to swap this in here for theta. So now we have arctangent of y over x is equal to 3 pi fourths. Now I'm going to isolate y by doing the opposite of arctangent, which is tangent. So I'm going to take tangent of both sides, right? Tangent, tangent, and that's going to cancel out with the arctan. Then I have y over x equals tangent of 3 pi fourths. And if we remember on the unit circle, right? 3 pi fourths is right out here. And tangent of 3 pi fourths is going to be, rad 2 over 2 divided by negative rad 2 over 2, aka -1. And then I'm going to multiply both sides by x, and I got y equals -x. And to graph this, this has a y-intercept of 0 and a slope of -1, which means the line is going to look like this going in both directions. And that's how you do it. Done. So for this one, we can run through the following test to see if it indeed has any symmetry. So for example, when I plug in negative theta here, if the equation kind of stays unchanged, then it might have symmetry to the polar axis. But it doesn't, because if you plug in negative theta, that becomes minus 4 sine theta. So that actually changes, so that one's out. Likewise for the pole, if I plug in negative r and it kind of remains the same, then it might have symmetry to the pole, but it doesn't, because if I negate the r, it does change the equation, right? So you see here, it wouldn't. Now we come to theta equals pi halves. So one way to test for this is plugging in negative r and negative theta, but it fails that test. But the other test is you could plug in r and pi minus theta to test that and see if that's the same. So if I plug in r, obviously that's the same. And then what is pi minus theta? So if this theta angle is in the first quadrant, pi minus theta is the same reference angle in the second quadrant. And the thing about that is Sine is positive in the first and second quadrant, so that would remain unchanged, and that would indeed have symmetry to theta equals pi halves. And we can check that in Desmos. You can see that the graph indeed does have symmetry about theta equals pi halves, which is like the y-axis. So that's how you do it. Done. So for this one, I just got a few theta values. And the reason why I chose these is these are going to be easier for us to calculate the R values mentally without using a calculator. Obviously, you can fill in more. I could test 45, 60, etc. But let's start with this, see how this goes. So if I plug in, and this is in degrees, by the way, right? So if I plug in 30, sine of 30 is 1/2 times 5 is 2.5. 1 minus 2.5 is negative 1.5. Oh yeah, I should have started with 0 degrees, by the way. So sine of 0 is 0 times 5 is 0. 1 minus 0 is 1. And then we got 90. Sine of 90 is 1. 5 times 1 is 5. 1 minus 5 is negative 4. And sine of 150 is the same as sine of 30. It's 1/2, so that's also going to be negative 1.5. Now we come to 180. Sine of 180 is 0, so that's 1. Sine of 210, that's negative 1/2. Times negative 5 is positive 2.5 plus 1 is 3.5. That's going to give us the same answer as 330 because it's the same reference angle, so 3.5. Last but not least, 270, that's going to be negative 1. Negative 5 times negative 1 is 5 plus 1 is 6. So let's do this kind of in order, starting at 0 theta, and that's at 1. Then we go 30, that's negative 1.5. Then we've got 90, but that's negative 4, so down here. Then we have 150, and that's negative 1.5, so we come back here. Then we have 180, and that's 1. Then we got 210, and that's 3.5, so right here. Then we got 270, and that's down here at 6. Then we got 330, that's at 3.5 back here, and there we go. And then we'd get back to 360, and that go back to 1. So now we can kind of connect the dots. Again, you can fill in more points if you want, but doing it in that order, we kind of come around like this, do a little loop-de-loop, and boom, not the prettiest, but that's basically the gist of it. So that's how you do it. Done. So for this one, I've arbitrarily picked some theta values in degrees that I can plug in that are going to be easy to evaluate mentally. Of course, we could do all sorts of more theta degrees. I could do using a calculator 10, 20, etc. But this definitely should be sufficient to get a rough idea of the graph. So plugging in 0, cosine of 0 is 1, 3 minus 3 times 1 is 0. Cosine of 60 is 1/2, so 3 times 1/2 is 1.5. 3 minus 1.5 is 1.5. Then cosine of 90, that's 0. 3 minus 3 times 0 is 3. Then we got 120. Cosine of 120 in the second quadrant, that's negative 1/2 times negative 3 is positive 1.5 plus 3 is 4.5. And then we have 180. Cosine of 180 is negative 1. So negative 1 times negative 3 is 3 plus 3 is 6. Then we got 240. Cosine of 240 is again negative 1/2 times negative 3 is 1.5 plus 3 is 4.5. And 270, cosine of 270 is 0, so 3 minus 3 times 0 is just 3. And then we get to 300. Cosine of 300 is again positive 1/2. Negative 3 times 1/2 is negative 1.5. 3 minus 1.5 is 1.5. Now let's plot out these points. So we start out with 0 and 0. Then we go to 60 degrees, and that's 1.5. Then we go to 90, that's 3. Then we go to 120, that's 4.5. Then we go to 180, that's 6. And then we go to 240, and we see 4.5 again right here, right? 4 and 5 in between. Then we got 270 straight down, we're at 3. Then we got 300 right here, we're at 1.5, and then again back to 0. So as we connect the dots, we get like this, coming around like so, and that's how you do it. Done. To find the absolute value of each complex number, what we're going to do is we're going to take the square root of the first real part squared, 4 squared, which is 16, and then we have negative 3, that coefficient squared. Negative 3 squared is 9. We add them together, we get the square root of 25, which evaluates to 5. That's the absolute value. Done. So the way we want to convert this is, first we want to find the absolute value of this. That's going to be the first part. So we're going to take the square root of the first term, the real part squared, plus the second part, which is negative red 3 over 2, that's squared. Then we're going to take the square root. 1/2 squared is 1/4. negative rad 3 over 2, which is the same as like really rad 3 because we're squaring it. Squared would be 3, right? Square root of 3 squared is 3. 2 squared is 4. So we got 1/4 plus 3/4, which is 1. Square root of 1 is just 1. So now we take that magnitude, and the shorthand is CIS, and then we need the theta value. So to get the theta value, what I can do nicely is I can take arctangent of this second value, this y value, which is negative rad 3 over 2, divided by the x value, which is 1/2. And that's actually in the unit circle, right? So when the y is negative and the x is positive, we're talking about quadrant 4, right? Now, if these two were positive, where sine is rad 3 over 2 and the cosine would be 1/2, right? Y is rad 3 over 2, x is 1/2. That would be 60 degrees or pi thirds, right? But since we're talking about quadrant 4, it would be negative pi thirds, right? We go backwards this way. So we have negative pi thirds for the theta, and that's how you do the conversion. Done. So to convert this back, the way we're going to do it is we're going to say that our x value is equal to r cosine theta, and y is equal to r sine theta. And my r value is right here. It's 3, and my theta value is right here, which is 40. So we're going to plug this into Desmos now. So for the x value, we get 2.3 rounded to the nearest tenth. For the y value, we get 1.9. So to put it back in the right format, we get 2.3, the x value, plus 1.9. That pairs with the imaginary number I. That's how you do it. Done. So to find the product, I wrote out the formula here that we have to follow. And then it's pretty straightforward, right? The product equals the two r values multiplied against each other, 6 times 10, which is 60, and then CIS, and then the sum of the theta values. So pi thirds plus pi 6, that's the same as 2 pi 6 plus pi 6, which becomes 3 pi 6, or simplifies to pi halves. That's how you do it. Done. So for this one, I wrote up the formula to get a quotient. So what we do is we take the ratio or the fraction of R1 over R2, which is going to be 27 over 9, which is 3, and then times the difference of the theta values. So 5 pi thirds minus pi thirds, which is going to equal to 4 pi thirds. That's how you do it. Boom, done. So for this one, the formula when you raise it to an exponent is r to the nth CIS n times theta. So r to the n is 5, that's our r, to the second power, which is 25, and then CIS, and then again it's 2 times this theta, 2 times 3 pi fourths, which is going to give us 3 pi halves. So that's how you do it. Done. So here's the formula for evaluating a root of z, right? So in this case, they want the square root. That means that n would equal 2. So we take this r value 25 to the 1/2 power, which is taking the square root of 25, which is 5. And then we have CIS, and then we have theta over n. So theta is currently 3 pi over 2 over n, which is over 2. So that becomes 3 pi fourths. Now, that's one of the values, and then we can keep adding values, up until we get to 2 pi. That's going to be kind of the cap. So we can keep adding multiples of 2 pi over n, which is 2 pi over 2, which is pi. So if we add pi to this, that's like 4 pi over 4. That gives us 7 pi over 4. So another possibility would be 7 pi over 4. And these are the two answers from 0 to 2 pi. That's how you do it. Done. So for this one, we have the imaginary and the real axis. So when we're trying to graph this complex number, the -1 is the real part. That corresponds to left or right. So we go left by 1, and then the 3i means we go up 3 on the imaginary axis. 1, 2, 3, which means this is my final point. Boom, done. So for this one, we want to eliminate parameter t to rewrite this as a Cartesian equation. So one way we can do this really quickly is, I see a sine squared. I'd love to have a cosine squared, because then we can use a Pythagorean identity. So watch what I'm going to do. I'm going to square both sides of this equation. I'm going to rewrite x of t as just x, because this is just saying x as a function of t. So it's fine. So I can square it, and I can say x squared equals cosine squared t. And I'm removing the negative because you square a negative, it becomes a positive. For y, I'm going to leave it alone, but I'm going to divide by 2, because then I have y over 2 equals sine squared t. The reason why I love this is because I know that sine squared plus cosine squared equals 1, which means, and since this equals sine squared, I can say y over 2 plus x squared, which is the same as cosine squared t. I can add these together, and that equals 1. And that is how you do it. Boom, done. So for this one, I'm going to make a little table to start like so. And we know that when t is 0, x is -2, y is 3. And when t is 1, x is 4 and y is 7. So first I'm going to come up with my equation for x in terms of t. So I basically have two coordinates in terms of a tx coordinate. I have 0, -2 right here. And then I also have 1, 4. And I'm going to use this to create an equation. So I'm going to subtract down to get the slope like I would normally do for any linear equation. -2 minus 4 is -6 over 0 minus 1, which is -1. That's a slope of 6. So x of t is therefore going to equal my slope times t plus my, in this case, x-intercept in terms of like what is x when t is 0. Just like for a regular equation, be like, what is y when x is 0? That is a -2 value, so I can say -2, and that's really good. Now for the y of t equation, so I'll do another two coordinates with t comma y like so. We've got 0 and 3, and then we'll also have 1 comma 7. And now I'm going to do the same thing. I'm going to get the slope. I'm going to subtract down. 3 minus 7 is -4. 0 minus 1 is -1. So -4 over -1 is a slope of 4. So we have y of t equals 4, the slope times the variable, and then plus that intercept, which is plus 3. So this is the system of parametric equations done. So for this one, I'm going to choose a couple of t values right off the bat. I'm going to choose 0, 1, and 2, and we're going to plug and chug. So into this equation, when t is 0, it's e to the 0th power, which is 1. Here it's e to the 1 power, which is basically e, which is like 2.71 or 2.72 will approximate. And then when it's 2, that's e squared, which is about 7.39. So those are those nice x values, and now the corresponding y values we're going to plug and chug. And let's do that in Desmos. But first we can do 0 mentally, right? 5 times 0 is 0, e to the 0 is 1. 1 times -2 is -2. When t is 1, we got -296.8. And when t is 2, we got this crazy negative number, -44,052.9. Okay, this one obviously won't fit, right? But we got two other points. We got decent points. So we know when x is 1, y is -2. So on our graph, that's like about here. And then when x is 2.72, maybe somewhere in here, y is like almost -300. So bringing it down, way down, going to be off the grid. So let's get one more value in the mix just so we can get something a little bit better. So if we have 0.5 for t, that would be like the square root of e, which is 1.6 approximately. And then for this one, we can see in the calculator, we get about -24.4. So that gives us another value that we can actually plot here. So 1.6, and then it's like -24.4, somewhere around here. And that's basically the gist of it. And then we can kind of plot it down like this. And you can see as the t values are increasing, we're going this way. So this is the direction of the graph as t increases. And then so in order to turn this into Cartesian equations, the last step, we're going to do a little plug and chug, right? So I'm going to start with the first equation, x equals e to the t. And then I'm going to isolate t. I'm going to take the natural log of both sides because ln of e just cancels out. So then we got ln of x equal to t. Now I can substitute ln of x in for t over here. And we get y equals -2e to the 5 times ln of x. Now what I can do with this using my logarithm rules is I can rewrite that as -2e because I can bring that 5 up as an exponent of x to the ln of x to the 5th. And then I now can say e to the ln of something. Those kind of cancel out and it just brings down that argument. So now it's y equals -2x to the 5th. That's how you do it. Done. A ball is launched with an initial velocity of 80 feet per second at an angle of 40 degrees to the horizontal. The ball is released at a height of 4 feet above the ground. Find the parametric equations to model the path of the ball. So first, let's do x of t, right? Because that's going to model the horizontal trajectory. And so to get that horizontal movement, it's that magnitude, the 80 times, and since we want horizontal, it's cosine of 40. And it's whatever this amount is times t, okay? So there is my horizontal movement, the x of t. And then for the y of t, we use our standard equation for gravity, right? Starting with, since this is in feet, we say -16t squared. And then the next part is the initial velocity times t. But now we're talking about vertical velocity. So instead of using cosine, I'm going to use sine. And then plus the starting height, which is 4. So we add 4. All right, so those are the two equations. Now it says, where's the ball after 3 seconds? So to get this, we need to plug 3 in for both of these equations to figure out both the horizontal and vertical distance. So let's do that in Desmos now. So rounded to the nearest whole number, the vertical distance is 14 feet, so it's 14 feet high. The horizontal is 184 feet. So we have 14 feet high and 184 feet. We'll just say forward, I guess, for the X. Last but not least, it says, how long is the ball in the air? So we want to know when this comes back down to hit the ground, aka I want to know when the y function goes to 0. So I can set this equation equal to 0. So let's do that in Desmos now. And what I did is I changed the t's to x's just so we can actually evaluate it based on the graph, right? So this is in the negative zone, a negative time value. That obviously doesn't make sense, but this is again where it hits 0. This is the valid number. So it hits it at, if we round to the nearest 10, 3.3 seconds, which means it's in the air for a total of 3.3 seconds. Boom, done. So for this one, we're trying to figure out if these are indeed equivalent vectors. And the way we figure that out is we want to see, you know, in our nice component form, you know, how much the x is changing from P1 to P2. It's going down by 8. And then here it's going down by 3. So let's see if we get the same thing here. From P3 to P4, we're going down by 8. So that's the same. And then here we're going up by 3, right? -1 to 2 is up by 3. So these are not equal. And because, you know, they're different. So not equal. That's how you do it. Done. So for this one, we're going to use the fact that u is that, v is that, and w is that to evaluate this expression. So I'm going to kind of use a little distributive property, and I'm going to plug in the vector. So v is 4i minus 3j, like so. And we're going to just basically treat this like an expression with a bunch of variables. And then u is 2i minus j, right? So you see how I'm just plugging in for u, and then plus w, which is -2i plus 5j. And then what I'm going to do is I'm going to distribute this. I'm going to distribute the negative. So then I got 8i minus 6j minus 2i plus j minus 2i plus 5j, like so. So then I'm going to combine like terms, right? -6j plus j is -5j plus 5j is 0. So the j's actually cancel out. Interesting. And then we got 8i minus 2i is 6i minus 2i again is 4i. So our answer is simply 4i, done. So here we're meant to find a unit vector, and the way we do that is we take the original vector and we just divide each component by the magnitude of this vector. And to get the magnitude, I take the square root of the first piece, that first coefficient squared, -3 squared is 9, plus the second coefficient, -1 squared, which is just 1. So we get the square root of 10. So I divide both of these by the square root of 10, and I get -3 over rad 10i minus 1 over rad 10j. Now they rationalize the denominators and the answers, which means I'm going to multiply top and bottom by rad 10. That's going to give me -3 rad 10 over 10. The reason why is because rad 10 times rad 10 is just 10, minus rad 10 over, again, same thing, right? Rad 10 times rad 10 on the bottom is 10, and we need our j and our I. That's how you do it. Done. So to get the magnitude of this vector, we take each of these components and we square them. We add them together and take the square root of that sum. So that's 9 plus 9, which is square root of 18. And we can simplify that to 2 times 9, which means we can take the square root of 9, bring it out as a 3. The rad 2 stays in. So that's the magnitude. Now, if we want the direction, we have to take arctangent of the y over the x, right? The second over the first. But -3 over -3 is just 1. But I want you to remember something. This might give me a certain answer in quadrant 1, but since they're both negative, this should actually be in quadrant 3. So if we get an angle here, we have to get the equivalent reference angle down here, and we do that by adding 180. But arctangent of 1, you might remember, is actually 45 degrees. So when we add it to get into the third quadrant, we add to 180, our answer is 225. So we have a direction of 225 degrees, boom, done. To get the dot product of two vectors, what you do is you multiply the coefficients of the i's plus the product of the coefficient of the j's. So 1 times 4 is 4 plus 4 times 3, which is 12. So 4 plus 12 is 16. That's how you do it. Done. So for these ones, we're going to do it color-coded, okay? So first we're going to do u plus v in red. And these two are actually already added together. We always say add from, head to tail, right? So u plus v is already shown here. We just need to connect the starting point and the ending point. So in red, there's u plus v. Now we need u minus v. And the interesting thing about u minus v is it's like adding u to negative v. So what I'm going to do is I'm going to make v negative by flipping it around, and then I'm going to add it like so to u, and now I'm going to connect the start and the end. And of course that's in blue, so there we go. Last but not least, we need 3v. Literally what I'm going to do is take the length of v as is and triple the magnitude. So I'm going to move it over here so we have a little bit more room so I can show you. So it's going down 1 over 2. So we go down 1 over 2 again, down 1 over 2 again, and we'll put that in purple so it matches. So anyways, that's how you do it. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.